All right, so why don't we kind of get started here? I don't know. Hopefully this will work. Yes, cool. Okay, so this is the CED. And so basically we're just kind of be kind of going down through it. So we're gonna try and cover as much as we can here. I have 2 hours until another lecture, so we're gonna try and speed run a little bit, but it should work out. We should be good. So yeah, we're pretty much gonna go straight through. We'll have some practice questions along the way. Yes, binomial is a fixed amount of trials. Yes, it's somebody asked me to cover the stats one, so I was like, you know what? Sure, why not? So um well hopefully. All right, so here it is. Unit 4. So the very first subtopic in Unit 4, 4.1 is really easy. So this is good. Um, so the first thing we can say, is, we can't say actually, is that patterns are uh, not just, they're not random just because they exist. So in other words, just because a pattern exists, we can't say there's something there, right? In other words, correlation doesn't equal causation. So for example, we see here a fun pattern between the number of what's this bachelor's degrees awarded in precision production and the number of parking enforcement workers in New Jersey. Obviously, this is not correlated, right? We can tell just by what they are that they're not correlated, but you see there's a nice like they line up, right? So just because there are patterns doesn't mean they're causing each other, right? So when we're thinking about stats, we really need to think critically about what we're looking at, right? So that's pretty much all this 4.1 is just to let you know that correlation does not equal causation. So any questions before we move on to 4.2? Cool. That's pretty easy, right? Just wait, just you wait. All right, here we go. 4.2. So, at this point, we want to see if we can actually estimate like real probabilities. Yeah, so we can do trees for like conditional probability stuff. But first, this is just going to start out real basic. So, a random process is anything that generates some results by chance. So, in other words, we don't know what the outcome is until it happens. So, for example, if we roll a die, we don't know that what we're going to get until we actually roll that die, right? Or if we are playing a game of Uno, right, we don't know what cards are going to be in our hands until, they are actually shoved into our hands, right? Um, and so that's kind of what a random process is. As far as an outcome, then, it's just one trial of a random process. So one roll of the die, right? An event then is just a collection of dice rolls, right? It's a collection of, how many different options we have, essentially. So moving on then, a relative frequency, we can kind of use that to estimate the probability then, right? So for example, if we're kind of on the side of the highway and we're looking at the cars that are driving by, we see that, for example, 4 out of 10 of them are white. Well, then we can say that as long as, we look at the same time of day, same highway, same place, that there's a 40% chance of a white car passing by. And so then when what we see here though is that 4 out of 10, 10 is not very large, right? So we don't have a very large sample size to go off of, which means that it actually could be much larger or much smaller than that. But if our sample size was much bigger, say 1,000, then we get a more accurate, say 39.1%, right? So it's actually a little bit less than that, 40% that we initially found. So do we have any questions? That's all that is just the law of large numbers. That's a mouthful, right? Law of large numbers. So that's something to kind of memorize. But yeah, any questions with this example here? We're gonna kind of take to the next step as well afterwards. No? Great. Okay. So do we have to know the vocab or just how to do it? It's good to know like if they say what the empirical rule is, right? That they're talking about like uh it's only good to know if it helps you identify what they're talking about, essentially. Other than that, if you're just kind of vibing with whatever they give you in the numbers, that's cool too. Yes, so the empirical rule is also the 68, 95, 99 and a half rule. That comes actually later in the course a little bit with continuous distributions. Yes, there is a link to the slide. If you go to this link, which I'll send, And then if you go scroll down to the stats, which is where we are here, and scheduled is that link right there. Okay. Yeah, absolutely. All right. So the idea though with this really with this subtopic is to use simulations. So in other words, it's really difficult, right? It takes a lot of time to go out and watch 1,000 cars go by, right? But if we know, for example, that say there's 45% of the cars out there are white, then what we can say is that we can kind of use a random number generator or a list of random numbers, whatever AP Stats uses, right? They make you use like a list of random numbers, I think, right? But either way, right, we can use some sort of randomly generated set of numbers to get a simulated kind of model, right? So, for example, if we randomly generate the 10 digits and say three of them, so let's see exactly what we want to do here. So say we want to see if the next 10 cars, out of the next 10 cars, if three or less are going to be white, right? Well, if we randomly generate this simulation, then what we can say is if three of them, if at most three are less than 45, three of the numbers are less than 45, then the trial is a success. And we can run that for a large number of simulations. So do we have to say 0, 0? Good question. So the only reason why you say 0, 0 is if your digits need to be double digit, right? So for example, if we are looking at 45, right, then we would need to have double digits because, I mean, unless you were going to do like a 4.5, then you could do a single digit, right? But yes, the idea is you have double digits so that you can include everything from 0 to 99. Okay, so let's talk about some probability stuff. So a sample space. Uh, Again, kind of a vocab word that is kind of nebulous, right? But really what it means is just all the possible non-overlapping outcomes. So if all outcomes are equally likely, then we can say that the probability of some event E is the total number of outcomes in E over the total number of outcomes in the sample space. So again, E is, so let's say, see if we can do some drawing here. So let's say we have our sample space. You guys can see this blue, right? All right, let's change it to like red. See if we can up the width as well. There we go. So if we have some sample space here called, S, right? We can call this sample space S. Then say we have a couple kind of uh, possibilities, right? So say we have 1, 2, 3, 4, 5, 6. Actually, let's leave it at 6, right? So let's say this is the event of rolling a die, right? So if we roll a die, we can either score a 1, 2, 3, 4, 5, or 6, right? And so it might even be better to label these 1, 2, 3, 4, 5, or 6, doesn't matter, right? Let's say we want to see if we can get a 1, right? What the probability of getting a 1 is. Well, all we need to do is, since there's all of these are equally likely, we can say we can box one of these and say that this is the probability of getting a 1. Or in other words, it's just one of these 6 possibilities, so we get 1 over 6. Does that kind of make sense? It's kind of like pretty straightforward, I think, kind of in these early kind of parts of this chapter. So, oh, and this was actually this is actually the question, right? So, the idea to get you guys to kind of grasp, right, is the sample space is just all the possible numbers, right? So the sample space for rolling a 6-sided die would be 1, 2, 3, 4, 5, and 6. Yeah, so if you guys want to take a guess at what the next part, if event A is roll at least a 4, then what do you guys think is that gonna be? That would be something P of A. You guys have to forgive my handwriting because I do not write with my trackpad very often. Yeah, so I'm seeing 3/6 and 0.5. That's exactly right, right? Because at least a 4 means a 4, 5, or 6, right? And so all we have to do is apply this formula and say, okay, there's 3 possibilities or outcomes in event E. And there's 6 total in the sample space. So that would be 3 over 6, which is 0.5. So questions on how this kind of formula works. Again, pretty bare bones to start out with, but then we'll ramp it up. Okay, cool. So let's do it. So let's do that and clear the drawings. So mutually exclusive events. So the probability that events A and B both occur, we can say is called the joint probability, right? So in other words, A and B, we can read it as, and that's that little, weird rainbow looking thing, right? The union is what it's called, right? So, oh, sorry, that's the joint probability, yes. So not the union. All right, so the joint probability, A and B, right? But if 2 events are mutually exclusive or disjoint, they can't occur together. So what do you guys, yes, it's the intersection, thank you. The name was escaping me. Not union. Union is or, which we'll find later. So can you guys think of some disjoint events? Maybe some examples? Winning and losing a game. Yeah, exactly, right? Or rolling a 1 and rolling a 2 in one kind of sitting, right? It was absolutely great. So then eating burger and drink soda. Yeah. You can't eat 2 things at the same time, right? Absolutely, right? So what about the probability of disjoint events? What do you guys think that would be? Like what would be our formula that we can use to look at that? No, there's no formula, right? It's just 0, right? Because if 2 things can't happen at the same time, then it'd just be 0. Exactly. So since you're right, if we want to find 2 events happening at the same time, we can add them together and we'll see that happening later. But if they're disjoint, then we know that they can't happen at the same time, right? So the probability of both of them happening would end up having to be 0. Hey, does that make sense? Okay. Okay. Yes. What D said is exactly right. All right, so let's go ahead and move to 4.5. So you see these first couple are going to go by pretty quickly. Conditional probability. This is where it starts to get fun, right? So if I know that one event has already happened, could that make it more likely that a different event might happen? And the answer is yes, right? So that's where conditional probability comes in. So what does this whole, mess of a formula mean? Well, how we read it is the probability of A given B. Exactly, right? That's exactly right. So um, if we know that B happens, what's the probability of A, right? And so we can find that out by looking at the probability of both of them happening and dividing out the probability that B happens, right? So really, this is looking for the probability of A, right? That's what it's looking for, the probability of A, given that we know that B has already happened or will happen, right? So let's see. Let's see if I have any examples in here. I do, but they're kind of later, so that's okay. We'll take a look at them when they come up. All right, so other forms of conditional probability. So let's take a look. If we know that this is the case, right? Can't we just multiply both sides by the probability of B, right? And if we do that, we'll get which one is it? This other which one is it? It's this one, right? If we multiply both sides by B, then that's what we'll end up getting, right? If we we'll get P of A and B equals P of A given B times P of B, right? So this is also equal to this, right? They're both the same thing. But these are also some good formulas to know if we want to kind of memorize formulas. Or I'm not sure if these are given to you on the AP Stats formula sheet, but if they are, then these are also good to know as well. One of you guys can tell me. Not directly, but the conditional one. Oh, perfect. It's given. Oh, you know what? Perfect. Thank you so much. Great. So exactly. So if this one's given, then we can derive the other ones by this, right? So if we ever need to see if something is conditional, we can use these formulas. All right, so independence is now the fun part, right? If I know that one event has already happened, you may be saying, well, this seems familiar, right? Could that make it more likely that a different event might actually happen? Well, the real answer is maybe, right? Because there are some events that aren't affected by each other. So these are called independent events. So let's say here's an example, right? Let's say if event A is your favorite food is pizza and event B is that you play the trumpet. Well, whether you play the trumpet doesn't depend on whether your favorite food is pizza. So therefore, the probability of you playing the trumpet, given that you eat pizza, well, again, we said this doesn't matter, right? So that's just going to be P of B, which is you play the probability of you playing the trumpet in the first place, right? Same thing here. The probability of you eating pizza, given that you play the trumpet, well, we said neither of them affects the other, so it would just be the probability of you playing the trumpet in the first place. Um, so is this kind of clear to you guys? Any questions here? We'll have some practice stuff coming up as well. So let me ask you guys this question then. What's the difference between independent events and disjoint events? Can two events be independent and disjoint? Several people are typing. I have a yes, I have a no, I have a no. Yes, question mark. Okay, so let's think. So I have a spoiler. All right, let's read the spoiler. Yeah, maybe because what? Yeah, okay. So um here's the question, right? The crux is if we have an event that is affecting another event, then that would mean that they are not disjoint. Sorry, that would mean that they're not independent, right? So if let's think about what a disjoint event means, right? If an event is disjoint with another event, then that means that having one event affects the other one because the other one, it makes the other one zero essentially, right? So uh, if we have an event that's disjoint with another event, then they're affecting each other, which means that they have to not be independent. So you can't have one that's both independent and disjoint. Does that make sense? So not independent, well, not necessarily, right? So for example, if your favorite food is pizza, the question, by the way, for the recording was, so not independent equals mutually exclusive. So uh, if, for example, let's take this example, right? Your favorite food is pizza and you play the trumpet. Those we said are independent. But if let's say something, let's say we have two events that affect each other, right? So we have, can anybody think of an example of the two events that affect each other? Let's see. If you are majoring in, say, going to school and pass a class, perfect. So if you go to school and pass a class, right? Uh, that doesn't necessarily mean that they're disjoint, right? Or studying and passing. Yeah. So, for example, if you study, then that doesn't mean that you're not going to pass class. It actually means you are going to pass class. It's just that studying affects passing, right? So it's not that you're passing affects it in a positive way, right? Yeah, exactly. As a positive relationship, right? But there also going to be a negative relationship, which is where the disjoint is. Does that kind of make sense? Where you can affect it positively, but you can also affect it negatively. So affecting it negatively and going so negative that it goes to zero is disjoint, right? Yeah. All right, cool. I love to see the yeah. I'll see what you want. Okay, cool, cool. Perfect, perfect. So let's take a look. And then we also said that since this is true, the probability of both of them happening is just going to be both of them multiplied together, right? So what we had here was this, but if we know that they are independent, then this term obviously would just go straight to be P of B, right? Or the probability of B happening. So with that, we can say, oh, did I? Did I get muted? Anybody else good? Okay, okay, cool, cool. So it's probably something on your end. Yeah, all right. So in other words, what we said then was this will go straight to P of B because they are independent. So we get that equation. All right, so what if we want to know the probability of either of two events happening? This is where we have the union, right? So this would be P of A or B happening. And what we'd say would be that this is the equation P of A plus P of B minus P of A and B. So my question is, if we have P of A, so let's see, we have P of A happening and P of B happening, and we want to see if either one of those happens, then we also want to see if both of them happen, right? Like if A and B happen, then we'd want to say, yes, this is true, right? But so then why are we needing to subtract out the case where they both happen? Or is addition right and is multiply? Yes, I'll answer that question 1 second. Yes. So all you guys are saying the same thing because it's overlapping. So it's not necessarily, it's kind of exclusive, but you'll see. So let's take a look at like the Venn diagram in this scenario, right? So we have A, say this is event A, right? And we want to see, let's say that this is event B, right? And then of course, this is the case where they overlap. Well, what we said was we want to see what the probability is if P or B happen, right? So that would be this probability, right? But when we add P of A, which is this, plus P of B, which I'll draw in, say, green, plus this, right? We see that this is actually getting added twice, right? So that's why we need to subtract one of those out. So what we really end up doing is this, right? We add P of A and say for example, A has the whole thing, right? Then we add P of B, but without the bit that overlaps. So is that clear? Oh, because it can also be like greater than one if you had exactly right. If you added P of A, say you had the probability of A was 90% and the probability of B was say, 70%, right? But the probability of A and B happening is like 80%, right? Well, in that case, you'd be thinking 9.9 plus 0.7. Well, that's way too much. You can't have more than one, right? Then you have to remember to subtract out the one case where they both overlap. That's a great point, Lingland. Thank you. Um, yes. Okay, cool, cool. So going back to a question that there was before, which was something, yes. So the addition and multiplication rules, right? That's just different names for the rules that we were talking about, right? So this was the multiplication rule. So this kind of rule here, same thing, this one, right? And this would be the addition rule. So that would hopefully that answers that question. Okay, so now we have some practice for you guys. Um, I think what I'll let you guys do is kind of I think there's 4 questions here, so we'll do the first two and then the 3 and 4. So I'll kind of read a question at a time, and I'll let you guys think about it, and then we'll get back together. So a card is drawn from a standard deck of 52 cards. Let event A be the card is a king, and event B be the card is a queen. So are A and B disjoint events? What is P of A or B? So this has two kind of sub questions, right? First is are they disjoint, and second, what's the union? So I'll let you guys think about the disjoint event first. Feel free to send your answers with a spoiler. Again, just for the disjoint event question, or both, since that was RS. That's what you gave me. That's fine. That works. That works. Why don't you guys try both of them? You can just I'll clarify that's are they disjoint and the union as well. So if you want to send both answers in one message, that's fine. All right, so let's give it a shot. Oh, great. Yes. Okay, great. So let's give it a shot. So, the first says, um, but this is just again, we're just doing the first question. So let's do this one. So the card, there's either a king or a queen, right? So first of all, I think almost everybody got this right. Are they disjoint events? Well, if you're pulling one card, you can't pull simultaneously a king and a queen, right? So that would mean that they are indeed disjoint events, which then means that we know that P of A, remember, the disjoint means that the intersection is going to be zero, right? So remember, that's what the disjoint means. So that's why that will be zero, right? But that doesn't account for the union, right? So this is the intersection, this is the union, right? So let's figure out what the union is by using our formula. So the formula that we learned was, um, I'll see if I can go back to it real quick. This one, right? So we have P of A plus P of B minus P of A and B. So we know that P of A and B is zero, is zero, right? So what we really just need to do is figure out what P of A is and P of B is and add them together. So we know that event A is the card is a king. Well, maybe I should have specified, there's four kings in the deck and there's four queens in the deck, right? One of each suit. Um, I feel bad if you're like an international student and you don't have never played cards and you need to do AP stats. I am so sorry for you. There are lots of things that you probably won't know. But yes, this is the case. So there's four kings and four queens, right? So that's going to be 4 over 52 plus 4 over 52, which is going to be 8 over 52. Or if you simplified it to 2 over 13, that works as well. So 8 over 52. That's a great 52 right there. I think okay, if they have if they have cards outside the US, I stand corrected then. I don't know. All right, cool. So a coin, so let's do number two. So a coin is flipped and a die is rolled. Let event C be the coin lands heads and event D be the die shows a six. Are they independent is the question now. So what is C intersection D? Sorry, so the answer for number one is yes, they are disjoint, and the A union B is 8 over 52. Yes, thank you. Yeah, so take a second, try and figure out number two. Okay, so um, let's take a look. So remember the way we find out if something's independent let's see if we can go back to it, is we look for this, right? P of A and B equals P of A times P of E. So if we can multiply P of A times P of B and we get what happens when they intersect, right? and we don't need to do this, then that means that they're independent, right? So let's take a look. Um, let's see. No worries. So let me go back to annotating here. So what we can do is take a look at the events. So let event C be the coin lands heads, which we know is going to be 1/2. And event D be the die shows a 6. And that's going to be 1 over 6 then, right? So this, of course, is just going to be 1 over 12 if we multiply them together. And what do we know? That is going to be the, the, the same thing as when they both intersect. So that means that they are indeed independent. Cool. Questions for this one? All right. That was a little bit easier. Let's take a look at number 3 and 4 here. So in a group of students, 60% take math, 40% take English, and 25 take both math and English. So what's the probability that a student takes either math or English? So again, this is pretty similar to the one we did before, right? So give it a shot and let me know what you guys think. Yep, RS, that's right. All right, so let's go over, and we'll kind of speed through a couple more of these. So uh, remember yep, not quite, but that's okay. We'll go over it. So the idea here with the union, remember, is to add both of them or add all of them, right? And then subtract sorry, I should say add both of the events, right? Math and English, and subtract their intersection, right? Because remember, we need to get rid of one occurrence. Where was it? Here, right? We need to get rid of that one occurrence with the overlap, right? So if we add, we get 60 plus 40 is 100, right? So 100. But we need to, remember, get rid of one occurrence of the overlap, which is that 25%. So we were going to get 75%. I've 0.35. So 0.5 is a popular answer. Let's see. So 0.35 plus 0.015 is 0.5. Um, I am not quite sure. Oh, maybe this is for number 4, yeah? That could be. Let's take a look. Um, or no, that's for 3. Okay, no worries. All right. So where are you getting 0.35 from and 0.15, if you don't mind me asking? Let's try and troubleshoot this a little bit. 0.6 minus 0.25. Ah, gotcha, gotcha. Yes. Okay. Yep. Okay. I completely understand what you're doing. So thank you for explaining. So, the idea is, remember, that we need to add both of them, right? So we need to add both of them together, the 60 and the 40, because remember that Venn diagram, you're adding both together first and then subtracting out the one overlap, right? So, that's why you want to add both of them together first and then take out the one instead of subtracting both overlaps, right? Because when you're subtracting 0.25 twice, what you're doing is actually taking out both of the overlaps. So that really what you're getting is that, you see what I'm saying? You're getting both of the things, but you're getting both events, but you're not getting the overlap. So yes, it's 0.75. Yep. Kind of is a little frustrating, huh? Sorry. But with more practice, it's you can start applying the formulas more, right? All right, let's try number 4, and we'll kind of keep it moving here because we do have a little bit more to get through. So a survey finds 570. Nope, that's not right. Let me double check what it's supposed to be. Um, let's see. It's supposed to be 70. So get rid of the 5. I wish it was 570, right? That would be crazy. No, it's just 70. So get rid, so it's going to be 70% of customers. Whoops, not this. 70% of customers uh, like product A, 50% of customers are under 30 years old, and 40% both like both product A and are under 30. Um, uh, yeah. Yeah, totally not fake self-reported numbers response. So yeah, but the question is, what is the probability a customer likes product A given that they're under 30? So this is, of course, our conditional probability formula, right? So give it a shot, see what you get. Yeah, so let's go over it. So what we have is um, 50% are under 30, 70% like the product, 40% are both, right? So what we need to do is with our formula here, which was this one here, we're looking for this one, right? We're looking for the probability of um, what was it? The probability that they like the product A, given that they're um, under 30, right? So what we can do is say the probability that they're both under 30 and uh, like the product divided by just that the probability that they're under 30, right? So if we go back, here it is. What we can say is we'll do zero point 0.4, which is the probability that they like both, divided by zero point 0.5, which is the probability that they are under 30, and we'll get zero point 0.8 as the answer. So questions with how we did that one. Again, just taking the formula and plugging in some numbers. So if we're given both, no worries, I can explain it. So remember the formula was the probability of A given B is equal to, this is how I remember it. The probability of A given B is equal to both of them, or their intersection, over the one that's given, right? Or the one that's we're look the conditional part. And the reason why I remember that, yeah, so the reason, good. Yeah, so this will be in the formula sheet. So you don't have to worry if you can't remember that. It's not a big deal. You can look at the formula sheet. Uh, but if we do that, if we do this, what we can do is both of them, which is 40%, because they both like product A and are under 30. If they're, that's 40% of them, so we can do zero point 0.4 over the probability that they like product B, which is, oh, sorry, that they're under 30. I can't get my words straight, right? But that's 0 0.5, so that this is 0 0.8. So egg, does that clear it up? It's pretty much just a plug and play with the formula. Great, great. Okay, so let us take a look at, yep, let's take a look at this next part. Yes, good tip here from RS is if you get something above 1 for a for a probability, then you're wrong. So take another double check there. Great. So let's take a look then at 4.7, which is Introduction to Random Variables and Probability Distribution. So this is where, I know I've been saying this is where the fun starts, but this is where it really starts, right? So what is a random variable? And I guess I should probably bold this. Let's do that now. So a random variable is a random process with a numerical outcome, right? And so all that means is you have it's made up of that events, right? And what we can see is that there's two types. There's continuous and there's discrete. So what are the differences, right? Well, continuous are, continuous data, we can say, are things that go forever, right? So you can, and they're, infinitely small intervals between them. So in other words, say, let's take age, right? We start out at age 0, right? And then we end at, infinity, so to speak, right? I'm sure there's some sort of you can't. There's no humans living at 150, right? But there's no set kind of end. So we'll say for as long as possible, right? That's not the point. The point is between say the years 0 and 1, there's infinitely small number of intervals between here, right? Yes, exactly. It probably just gets lower and lower that you actually live there, right? You're exactly right. The idea with continuous, though, is that there's infinitely kind of small intervals between any sort of arbitrary uh, counting mechanisms, right? So 0 and 1, for example. Whereas with discrete data, we're looking at discrete categories, right? So, or for example, if we're saying, the number of pages in a book, for example, right? You can't have, say there's, 0 to, again, there can be infinity number of pages, right? Or a lot of pages, right? Or a number of people, right? That's another great one, right? But you can see that the page numbers jump from 0 to 1 to 2 to 3. There's no infinitely number of intervals that you can get between there. So does this kind of difference make sense? Because that's something that they will like to test on. Is that cool? Does the kind of infinitely number of intervals between whatever makes sense? All right, I'm gonna take that as a yes. So what does discrete mean? Well, that's what we just said, right? It's a countable number of values. So for example, another one is 12 notes in music, right? A through G. And it's not an infinite number of intervals between them. Again, each value has a probability associated with it. So for example, when this, if you're looking at, say, a Mozart concerto, right? You can have a distinct number of note A's, right? Thanks. That's just something that came up, right? So yeah, you can have the distinct number of A's in there, right? If you absolutely feel free to fill out the feedback form. If you want to leave any feedback, you're welcome. I appreciate, positive and also criticism as well. So yes, please do that. So anyways, yes. So each value has a probability associated, right? So you could have 50% of the notes are A in a given piece or something, right? And then the sum of the probabilities over all the possible values from A to G, for example, that has to be 1. So if we look at what exactly we mean by this, a probability distribution can be represented by a graph, right? And essentially all that's showing is the different probabilities at a given point, right? So for example, and actually we'll see one in the next slide, so we can look at them. And then a cumulative probability distribution is all that's saying is as you're going up, instead of giving discrete kind of probabilities, you'll have a cumulative distribution. And you'll see what we mean when we take a look at this one. So here's a question here. We want to consider the probability distribution of the number of earthquakes X in the US that are 7.5 on the Richter scale or higher in a given year. So the first question we have is, what would the cumulative distribution have for the entry when the number of earthquakes is 1? So here's what I mean by cumulative distribution, right? Here's an example. So all that the cumulative distribution is saying is, instead of discrete kind of probabilities for each number of earthquakes, we're going to add all of the previous ones, right? So if we're looking for the number at 1, the cumulative distribution is going to have 0.4 plus 0.5, right? So that's going to be 0.9 for the cumulative distribution at 1, right? So what do you guys think all cumulative distributions have to end at? What's going to be their max number at the very last kind of cell here? 1, right? Exactly, because they're going up, right? So in this case, the cumulative distribution is going to be 0.5, 0.9, and 1. Cool how we did that? All right. So the next question says, describe the shape of the probability distribution P of X. So here is the probability distribution here, right? What do we see? How do we see that the values are distributed? Are they pretty even or are they not even? What do you guys think? Not even, right? Because zero point 0.5 is clearly skewed compared to zero point 0.1, right? So if we take a look at it, you're exactly right. It's going to be skewed to the right, something like that, right? Great. What would the probability be that that one or two earthquakes happen? So how would we do this one? Well, one or two is the union, right? Yeah, exactly. So um, 0.4 plus 0.5. 0.5, remember, that's 0, right? Uh, just add P of x1, P of x2 at 0.45. Yes. So RS, that's exactly right. Um, but I understand why you guys are going with other answers. Here's how we would go about thinking about it, right? Is all we need to do is add them. And let's think about how we would do it if we were using the formula, right? Remember, the formula is P of A plus P of B minus their intersection, right? So let's do that. Well, P of A, which is 1, is 0.4, and P of B is 0.1. So, and before we do the equal sign, we need to subtract their intersection, right? But here's a question for you. In a given year, can we have both one and two earthquakes? No, right? So that means they're what? Disjoint. Absolutely, right? They're mutually exclusive. You can't have yeah, dishing. Exactly, right? They're mutually exclusive, right? So you can't have more than one earthquake, or sorry, you can't have more than a set number of earthquakes, right? So in other words, you can't have one and two earthquakes, which means that they're disjoint. So their intersection then, their probability at their intersection is 0. So we can say that 0.45 plus 0.01 is zero point 0.5. Great. So let us now look at a more fun problem. This is more of something that you might see on an AP exam. What would be the probability of two earthquakes in 2 years? Right? So we're not looking at, remember, this is the probability distribution for 1 year. So what we need to look at is a probability distribution for 2 years now. Was this a geometric distribution? Not quite. So all this is right now that we're looking at is a probability distribution. But what we'll do later is, and we might bleed into 9 o'clock, that's okay, is we'll look at the probability, sorry, we'll look at geometric distributions. But for now, we need to figure out what two earthquakes in 2 years is. Remember, this is 1 year. So what do you guys think? I'll leave it to you guys for a little bit, maybe a minute or so to kind of think through it. Oh, yes. Altanus. I almost said Atlantis. But nice. You if you want to put your answer in a spoiler, feel free. Let's take a look. Yeah, that's absolutely right. Good job. Do you want to tell me how you got that? Yep, RS, you're absolutely right. Sure, great. Let's hear it. It might be easier to have you type it out. I don't know if I can. I think you have to have lecture perms or something to talk, unfortunately. I wish I could just give people mics, but I can't. So if you don't want to type it out, that's fine. I can do it, but up to you. So I have P0 times P2 squared, it seems, plus P1 squared. Yes, that is very close. Okay, no worries, no worries. So let's take a look. So the idea is if this is the lecture, oh sorry, if this is oh perfect, let's take a look. Ah, yes, yes, great. So if you guys want to unspoiler what Altanus, is that, am I saying the name right? Altanus? Perfect. If you want to unspoiler what they put, then that's absolutely right. So what they said was P0, which is zero point 0.5 times P2, which is 0.1. So in other words, what that's saying is in the one case where we have the first year is 0 earthquakes and the second year is 2 earthquakes, right? That's going to be um, zero point 0.5 times 0.1. And we need to add to that the other case, or the other cases, I should say, which is where we have 1 earthquake in both years, right? And that's going to be P1 times P1. And then finally, we need to add to that the last case, which is we have 2 earthquakes in the first year, 0 earthquakes in the second year, which is again 0.1 times 0.5, right? So what you can do then is say that if you multiply all those cases and then add them together, you get that 0.26. And I think, yeah, there it is, right? So that's exactly right. Good job, guys. Let's take a look. So the next part, mean and standard deviation of random variables. So this is kind of the general case on how you find forming the jump scare. Yeah. So this is kind of the general case on how you find the parameters for random variables, right? So we have mean and expected value. Again, this is for discrete distributions, right? So for discrete distributions, we have the sum or the summation of each it's not very stuff. Yeah, okay. So for the mean and expected value, we'll have the summation of each individual value times their probability, right? So it's actually not that bad. Let's take a look. Here it is. Yeah, right. Okay, so let's do this. Let's do the mean for here. So all we need to do is add each of the individual values times their probabilities, right? So 0 times 0.5, 1 times 0.4, and 2 times 0.1. So what's that going to be? 0.6, right? You remember doing this? Good, great. This is the goal, right? So that it's pretty simple to find the mean, right? The standard deviation is where it gets a little bit messy, right? So let's take a look how we would do that. So for again, this is for discrete random variables. What we would need to do is find the distance that this value is from the mean, right? Remember, this is what the point of standard deviation is to find the distance from the mean, right? So we're looking at the distance from the mean squared, and then times the probability that you're going to have that distance, right? So again, just to kind of reiterate, we're looking at the squared distance of the individual observation from the mean times the probability that you're going to get that distance. And once you add those together, you'll get what we call the variance, right? And then, of course, we need to square the variance to get the standard deviation. So what we would do here, we would say, well, we're looking at 0.6 minus 0 squared times 0.5, right? And then 0.6 minus 1 squared times 0.4. 0.6 minus 2 squared times 0.1. Now, and you add all those together and you have to square root it. So can somebody remind me why we have to square root it? I think I may have just said it. Why not just use a calculator? You could use a calculator, but it's good to know what we're doing, right? Yeah, so variance is the squared, right? So all we need to know, remember, is that the standard deviation is always the square root of the variance, right? So no matter if we're looking at the sample size or the sample or the population, it doesn't matter. It's always going to be the square root of variance, right? And so this kind of gets into these Greek symbols, which is the Greek symbols, remember, are the population parameters, right? So if we're looking at an individual sample, then we're looking at the X or the Arabic numerals, right? So for example, here, this is a sample of 1 year, right? But if we're trying to estimate the population, or in other words, the mean of every year, or the standard deviation of every year, then we need to use the Greek letters. So again, just a small annotation thing, but that's something that kind of caught me up when I was taking AP statistics. All right, so let's take a look at these ones. We did that mean and standard deviation already. If we interpret these values, we get in the long run, we expect 0.6 earthquakes per, sorry, this should be year. Let me change that real quick. I originally had this question as a 6 month period, but it's actually a year. All right, so in the long run, we said 0.6 earthquakes per year, but that value could vary by, again, 0.6 something, right? I don't remember what exactly it was, but earthquakes. And so now we can use these to actually describe the center and the spread of the distributions, right? So the center is it's going to be centered somewhere around 0.6, and the spread, again, is going to vary by about 0.6 earthquakes. Again, the units are important to have. Really, what they're looking for in the interpretations is that you actually get the units, right? So any questions with this example before we go into combining random variables? Cool. Let's do it. Oh, there we go. 0.6633 if you did it. All right, so combining random variables. So we have a different scenario here. So if we need to transform one random variable to another, then here's how we do that, right? If we're multiplying by something or dividing, then that would apply to both the mean and the standard deviation. If, though, we're adding or subtracting, then that would be the mean only, right? So for example, given the probability distribution of time it takes in minutes for a specific restaurant to make an order, we need first should find the mean and standard deviation. So let's do that. I'll leave it to you guys for this one because I kind of walked through the last one with you guys. I'll leave it to you guys to find the mean and standard deviation here. Again, put it in spoilers if you want, and then we'll get back together and do a transformation of this. Don't have a calculator. That's not a problem. Let me send you this calculator here. This is it's kind of um a little bit cheating, but that's okay. Who cares? Sometimes you need to cheat a little bit, but don't tell people that I said that. Don't cheat in like tests and stuff, but cheating on homework for I mean, don't cheat on homework if it's graded, but if it's just for practice, like this is, you know. If it's graded though, then don't do that. That's not very Sigma. You're welcome. All right, so let's take a look. So if you guys have not finished yet, that's not a problem. We can kind of walk through because we're believe it or not, I think the last couple subunits are going to take a little bit. So we're kind of you know what? I take it back. We're doing great on time. Don't even worry about it. I'll let you guys finish and type your answers. Don't worry. Let's take a look. Yep, all of you guys are right. So let's take a look at what it is. So um, remember that how we do this is multiply 5 times 0.15 and then add to that 10 times 0.26 plus 15.131, so on and so forth. And that's going to get us our mean, right? Our standard deviation then is simply 5, the mean minus that 5, or you could also do the 5 minus the mean. Either one's going to be fine, right? Because you're going to eventually then square it and then multiply it by that probability and add all of those together and square root that whole thing. So it should be what you guys said, 14 for the mean and 5.7879 for the standard deviation. So let's take a look at this next bullet point, which is this combining random variables idea. The restaurant fires a chef because the economy is bad, you know? And so this is now going to count for a 6-minute delay in every order. So we need to find the new mean and standard deviation. How many significant figures should you use for stats? I don't know if there's actually I think there's a very strict rule. I'm like remembering a very strict rule for stats, but I don't remember what that rule is. I think it's three, but I could be wrong. So maybe somebody would know. I think 3 is usually safe. Chem is the strict 3. Okay, so I think 3 I think 3 for in general is pretty good. Gotcha. Chem is a strict one. Good to know. So yeah, I would go with 3. Great. So I have one answer of 20 and 5.79. I think that's right? Because it's a 6 minute delay, right? Which means that we're only adding 6 minutes to every order, right? So that's adding, which means we're going to apply that to the mean only. So you're absolutely right when you say 14 plus 6 is 20. And then, of course, the standard deviation is staying the same. So now, using that same data, so the new mean is 20 now, we want to report our times in seconds rather than minutes. So we need to find the new mean and standard deviation. Why they want to report in seconds? No clue. Don't ask me. But how do we do this? Unit conversion trauma strikes again. Yep. Yes, there still is the delay. So this is going to be the new mean is 20. Dimensional analysis. You're exactly right, except hopefully in the stats world, this will be a lot easier than they're going to make you do in like the chem world or bio or whatever. Yes, so times by 60, that's exactly right. So all we're doing then, I won't make you guys do it, is timesing or multiplying the 20 as our mean times 60 to get 1,200 seconds, which of course is good for the mean, but we also need to do that to the standard deviation because we're multiplying, right? So that would become 347 point something. Yeah, there you go. 274. Great. So let's also take a look now if we want to combine two different random variables together, right? So in other words, we have some distribution that's going to tell us something, and another distribution is going to tell us a completely different thing, and we want to combine them together, right? Well, um, if we know, well, first of all, they have to be independent of each other, right? If one independent variable, sorry, if one variable is dependent on another one, for example, if your grade is dependent on your class participation, thank you for whoever mentioned that one way back when, right? Then we know that if we try to combine them together, then it's going to be really difficult uh, because one is kind of depending on the other one, so we can't really combine them into one thing, if that makes sense. But if they're both independent, then we can kind of combine them into a shared distribution. So they have to be independent. The next thing is that the means of both variables can simply be combined by adding or subtracting, right? So, for example, uh, if we're looking at the difference between two independent variables, then what we can say is just the mean difference is them being subtracted, right? Then, of course, if we're looking at the standard deviation, though, that's where it gets a little bit more tricky. So the first thing we need to do is convert it to the variance. So this is why I kind of made a point to mention the variance is because we need to know what that is in order to do it, right? So in order to get that variance, we need to square the standard deviation because remember the standard deviation is the variance under a square root. So to cancel that out to get back to variance, we square the standard deviation. Then, of course, once we're at the variance, that's where we can start editing, so to speak. And of course, we can't subtract the variance. The reason is because the standard deviation. So, for example, if I have a curve, right? This is more of a bell curve. It's a normal distribution, so it's going to be something that you guys might learn in Unit 5. I don't know if you guys are there yet or not, but the idea is you have a standard deviation. Whoa, let's not do that, right? Standard deviation is like this, right? Now there's positive to it, right? But there's also negative to it, and it's added together into this one big kind of unit, right? So if we can't ever have a negative standard deviation, right? Which means that if we were subtracting things from it, we could potentially get that to be negative, and that's not what we want, right? We always want this to be a positive. So we can't ever subtract things from the variance or the standard deviation. Z-scores can be negative, but that's not necessarily specifically talking about the standard deviation, right? So uh, at that point, then we always add them together no matter what, and then we go ahead and convert back to the standard deviation by squaring it. So let's clear this and look at an example. So suppose a restaurant knows the following information about their sales. They sell on average 35 appetizers per night with a standard deviation of 2 appetizers. Then they also sell an average of 50 entrees per night, which with an standard deviation of 5 entrees, and they sell an average of 20 desserts per night with a standard deviation of 4. So the manager wants to know the mean and standard deviation of the total amount of dishes they sell per night. How would we find it? So the total amount of dishes implies what? Add, right? We need to add them together. So we can see right now we have 3 different random variables, right? But we will need to add them all together to get the total amount of dishes they sell. So in order to do that, then all we need to do is add the means together and then square. Remember, we need to square each of these. So 2 squares to 4, 5 squares to 25, 4 squares to 16. Then add those together and do a square root of that, right? So what we should get is exactly what Langland said. 100. Sorry, not exactly what he said, but close to it, right? At least the standard deviation was right. The 35. Remember that we have to add the 35 to the 50 and the 20, right? So that's where we're gonna get the 105. Sorry, not to call you out. I thought I read at 105 and I actually read 35. So that's my bad. um, but hey, it's close, right? You got the more tricky part right. So it was probably just a small mistake or something. Yeah, there you go, 105. Perfect. Okay, so that's how we would do that. Let's take a look then at this example. I want you guys to try and do this one. This is a little bit more tricky. The manager wants to know the mean and standard deviation of how many more entrees he sells than desserts and appetizers combined. So how would we do this? So try it out on your own. If you have a calculator with you, you're welcome to use it, although you probably don't necessarily need it for this one. So give it a shot and put your answer in a spoiler. How are we feeling about it? It's a bit tricky, right? If you're just joining us, welcome. We're working on a quick question. Yes, it is recorded. No worries, no worries, no problem. All we're doing right now is we're trying to figure out what the question or what the answer to this question is going to be. And the question itself is how many more entrees does this restaurant sell than desserts and appetizers combined? You can type it in here if you want as a spoiler. You don't have to. I'm gonna give us a few more minutes here. Yes, RS. You're right. This is why it's a little bit more tricky, right? But now the question is the standard deviation now, right? Yes, yes, it is. Nice. Again, welcome in if you're just joining us. I'm gonna give it like one more minute here on this question, and then we're gonna kind of go over it. So if you want to give it a shot, you're welcome to. This is remember 3 separate random variables that we're trying to combine. Ah, that's the question, Langland, isn't it? I'll tell you it's the second one that you said. All right, let's give it a shot. Let's see how we're going to do this. So, um, the question is the manager wants to know the mean and standard deviation of how many more entrees he sells than desserts and appetizers combined. So, first things we need to do is figure out, well, what's the random variable of the dessert and appetizers combined, and then subtract that from the number of entrees, right? So let's do that. So first things first, like we said, we need to figure out the desserts and appetizers combined. So for the mean, we know that all we need to do is add them, right? 50 plus 20. Sorry, desserts and appetizers, 35 plus 20, right? Um, so what we can say then is that the mean of the random variable with desserts and appetizers combined is 55, right? And so now when we subtract that from entrees, we get 50 minus 55, which is actually -5, right? So remember how we said that the standard deviation can't be negative, but the mean actually can be, right? So we're all good there. 55, so that would be a -5 as the mean. And when it says to interpret your result, what I meant by that was, well, what does it mean if the result is negative? So what do you guys think? What does it actually mean that the result is negative? And I think RS said that before. All right, yes. Let's see. So you're selling less entrees than the other stuff combined. Exactly, right? There are five fewer average entrees sold than appetizers and drinks combined. Exactly. So there's five less serving. Yep. So what's really happening is let's see. In the long run, we expect the restaurant to serve five fewer entrees than appetizers and desserts combined, though it can vary by 6.7 dishes. That's exactly what I would hope to see on an AP exam. That would score you like a 5, right? So in the long run is key as well, right? Because we want to know um, that we're looking at the population, right? So because the means that we're finding, I'll kind of run through what he means by in the long run and the whole thing, right? So remember that these means and standard deviations, we're using the Greek letters, right? Which we said was the population or in the long run mean and standard deviation, right? So same thing here. We're using the Greek letters, which means that we're looking at the long future, right? So in other words, aggregated across much of the future, right? Or the population that you're looking at. So that's why he says in the long run, we expect the restaurant to serve five fewer entrees than appetizers and desserts combined. So what that means is looking at the mean as -5, what that tells us is that they're actually selling more appetizers and desserts than they are entrees, right? So when he says to serve five fewer entrees than appetizers and desserts, that's what they mean, right? So and then at the end they say though it can vary by 6.7 dishes. So that's the uh, standard deviation then, right? So the standard deviation, which we didn't really talk about, well, let's do it. We know that the standard deviation, we can't be negative, right? We only can add to the variance, which means that if we're only adding, then it's actually going to end up being the same standard deviation, that we saw here, right? 6.7. Um, yes, I'm not sure Dragonfire if you can do that, but I would if I was grading it, I would say probably, right? Because it's the same idea, right? You're with repeated sampling and very with a lot of samples, right? The whole population worth, then you'll get those results. Um, so, anyways, standard deviation we said cannot be negative, so that would be you'd have to add them all, right? Or you have to add the variances together. And so if you can only add to the variance, then really if you combine them, no matter how you combine them, they're going to be the same standard deviation. So that the answer is going to be this. -5, you sell more appetizers and desserts than entrees, and the same standard deviation. Okay, any questions with how we did this one before I move on to 4.10, which is the binomial distribution? All right, let's do it. So a probability distribution in general, first of all, is simply kind of using the rules of probability or an estimated simulation. And it kind of uses the random number generators to find the distribution that you're kind of sampling from, if that makes sense. So at this point, we're going to talk about two different distributions that commonly occur in the real world. Oh, you skipped this part. That's not good. Let's look at this part. So the first distribution is the binomial distribution, which can only be applied when you have these kind of three things laid out, right? The first is you have a set number or n number of repeated independent trials. So in other words, the results of one trial doesn't influence the result of other trials, right? If that's the case, then we're good with this step one. The second part is that each trial has two specific outcomes. For example, if you're flipping a coin, right? You can only have heads or tails. So two options, yes or no, right? You either get the deal or you don't, right? So that's the kind of second kind of rule here is first is needs to be specific number of independent trials with each trial having two possible outcomes. And finally, then the last rule is the probability of success P must not change. It must be fixed and it can't be changed from trial to trial, right? If this is the case, which is the case a lot, then you can actually use this distribution and it's much nicer, right? So this scenario can be represented by a random variable from the binomial distribution, which we will call x. So here is this kind of big, crazy looking formula, right? Don't worry about that. Here's what the formula for this thing is. Let's just do an example and we'll figure it out, right? So we're watching cars go by again, right? This is all the way back to the beginning, kind of full circle moment here, right? And we note that the chance of a white car passing by is 45%. We observe then the next 10 cars and are wondering what the chance that one out of the 10 cars is white. Yes, so this is on the reference sheet. Do you know if this is on the reference sheet too? The choose? This sort of just kind of for my reference. No? Okay, cool. Good. So this is good to know then. So gotcha. No worries. So let's take a look. So I think if we really understand what's going on here, then we'll know, then we can kind of apply that to the formula and kind of understand what's really happening. Yes, they could ask you, for example, they could ask you a question just like this, but have the answer in terms of the formula. So you'll see what I mean. You'll see. So let's take a look. So we are watching cars, and we know that the white car rate is 45%. And then we observe the next 10 cars. So what's the chance that one of the 10 cars it was white, right? Or the next 10 cars is white? Well, we know we have one car, say two car, three car, four car, 5 car. We have 10 cars, right? 7, 8, 9, 10. So these are the next 10 cars that we're looking at. Yeah? So what we can say then is if one of these cars is white, say this car here was white, and the rest of them were not white, then what we would say is, well, this specific, and remember, because they're all independent, we can say this specific trial or this specific car had a 45% chance of being white, right? 45% chance. This car had, well, this car wasn't white, right? So what was the percent chance that this car was not white? 55, right? It's just the complement, the 1 minus 0.45. So this then has a 0.5%, sorry, 0.55% chance, right? Exactly. And so what we see then is all of these are going to have a 0.55% chance of not being white, right? And what we can say then is because they're each independent, right? And remember all the way back to the very beginning, right? Where we said that if they're not independent, we can do this. We can multiply them together to get the probability that that this event happens in this specific way, right? So if we do that, if we say, okay, we're going to multiply all of them together, right? To get the answer, and we'll say 0.45 times 0.55 times 0.55 times 0.55, so on and so forth, then that will lead us to one instance of how this could have worked out. So are we all on track so far? We're all kind of understanding how this is one instance of what could have played out, right? 0.45 for this car and then 0.55 for all these other cars, right? Great. Okay, so now here's the fun part, which is where this choose part comes in. So this was, we agree, one instance of how this could have worked. Yeah. The second, another instance could be, say, this car was the one that was white, right? So say this is 0.55, and this is 0.45, right? And then all the rest of them are 0.55. 1 second, I see the question. Give me 1 second here. And then all the rest of them are 0.55. So we agree that this is another situation that could have happened, right? So let's see, what unit is the sampling distribution stuff and proportion tests? I'm not gonna lie, I am not sure, but if you look at the CED, if you just look up on Google like AP stats CED, you'll find that and you can look through that and figure out where that is. Does that help? Cool. All right. So this is another opportunity or another kind of chance that could have happened that would satisfy what we're looking for, right? One of the 10 cars was white. So how many chances are there then that would satisfy this condition, 1 out of 10 being white? What do you guys think? So at first we said this was the one that was white. Then we said this was the one that was white. And remember, we're only looking for one that's white, right? So how many other cars do we have that could be white? Yeah, right. Exact. You could say n, right? N number. But yeah, 10, right? There's 10 total possible white cars, right? So what we'll say is that this 10 choose one, or in other words, we're looking at out of the whole 10, we want to choose one to be the white one, right? This this kind of idea or this notation is simply the number 10, right? And so now looking at this, we can say go back to this formula here. We can say that this 10 um, so this 10 choose one was 10. And then what we did was we multiplied the probability of success, or this P, which is the 0.45, right? The probability that we had a white car times the number that we're looking for, right? We're looking for one white car. And then the rest of them, we said we want to be not white. So we did 0.55. So that would be then the rest, which was 9. So there were 10 possibilities of this stuff, right? Of this way occurring. Um, So yes, this would be your answer. Yes. Let me catch on with some chat here. So I'm not in this class, but it's nice to get a head start for junior year. But wouldn't the answer for the car be 4 or 5? Or sorry, wouldn't the answer for the car be 45? Yes. So that's a great question. So um, this idea is that there's one white car that's 45%, right? So there's one white. If there's the chance of any individual car being white is 45%, right? So for example, this one individual car could have been white or not white, but the chance of it being white is 0.45. But now we're looking at an aggregate of all 10 possible cars. And when we do that, what we see is if we're only looking for one to be white, then we'll have 0.45 times 0.55 for the rest of them, right? So that's then this formula of 0.45 to the 1, right? We're looking for one white car times 0.55 to the 9, right? 10 minus 9. Or sorry, 10 minus 1 is 9, right? And then what we said was, well, this green option was one way it could have happened, right? This red option, if this was the one that was white, where this one was 0.55, 0.45, and the rest of them 0.55, that was another way that could have happened, right? Which means that this whole formula would work because this 10 is giving us all 10 different options where that could have happened. Okay, so it looks like you guys are right on the money. Let me double check the answer here. Yeah, so Langland got it absolutely right. And Na got it right as well. Hi, absolutely right. Uh, so Hi brings up a, oh, sorry, it was Na that brought up a good point. So you could do this on your calculator, right? If you did the command binom PDF, right? And then you set the trial number to 10, the probability of success to 45, and the number to 1, then you get this answer, right? This 0.27, sorry, 0.0207, right? If you want to do by hand, that's fine too, but it's a lot easier on the calculator. So I would definitely try and learn that. But these are kind of small examples to learn. So any questions with how this kind of worked? It's really an interesting and cool way to be able to model stuff, right? All right, see somebody's typing, so let's give it a second here. I hate combinatorics, but binomials aren't too bad. Yeah, I agree. So the chance is, well, if we have this as our final answer, this is the probability, right? So we would multiply by 100 to get move the decimal point two places. So we get 2.072. So it'd be 2.7, sorry, 2.07%. Does that make sense? Yeah, exactly. So there's a 2% chance. Okay, no worries, no worries. So I think I erased the stuff again, but oops. But I understand the formula. Great. So as far as the interpretation, then it sounds like is where the question is. Yeah. So if we understand how we kind of get this number in the formula, then the interpretation is simply that 2% of the cars passing by out of the next 10 cars, sorry, there's a 2% chance that the one car out of the next 10 cars is white. So if we get this number, 0.0207, multiply by 100 to get 2%, so you get that 2% chance that one of the next 10 cars is white. Any other questions? Here's the formula for this kind of choose thing. If you guys know factorials, you're welcome to use this. I kind of chose an example with 10 choose 1 that was kind of more simple to kind of gauge and kind of learn from. But there's going to be a lot as you kind of start upping the k value here. There's going to be a lot more kind of scenarios that you're going to have to consider. And in fact, that number of scenarios is going to be given by this formula here. So again, if you want to do by hand, you're welcome to. But as Na said, binom PDF is a good way to go on the calculator. All right, so let's try this one. So this is more of a chance. Sorry, this is more of a question that they could ask on like a AP exam. So you're watching the cars go by again, and note that the chance of a white car is still 45%, and you observe the next 10 cars. So what's the chance that 8 or more of the cars are white? So again, we still fit this idea of fixed number of trials, 10, independent trials, right? The cars don't have effects on each other. And it's only either white or it's not white, right? So we can still use the binomial distribution here. It's just how can we apply it to get this what we want, right? 8 or more of the cars are white. So does anybody have any ideas about how we might solve this? All right, so let's see. So let's see. You said 10 choose 8 times 0.45 to the 8 times 0.55 to the 2. Yes, there is more, right? Because what that was, let's see if we go back to the formula here, is this is to the 8, sorry, 0.45 to the 8 times 0.55 to the 2, that's only getting you the specific value for 8 cars, right? But we want at least 8, right? 8 or more. Yeah, High's got it. Absolutely right. Let's see. Mm-hmm. Yeah, you guys are on the right track. So, um, here is exactly how we're gonna do this, like you guys are saying. So I'll give it a second because there's a lot of people typing. All right, here we go. So, um, is 10 choose 8 another way of saying 8 out of 10 or something similar? So it's something similar. It's not quite saying just 8, right? It's saying the number of ways that we can split 8 among 10, if that makes sense. Uh, Difference between yes, yes. Yes. Okay. So okay. Yeah, so this is what's called a CDF, right? So uh let's see. Yeah, it's how many ways you can have 8 objects split among 10. So this is what a CDF is, right? So the idea with a CDF or cumulative distribution is just like how we're talking about the probability distribution and the cumulative probability distribution, right? The PDF and the CDF. So remember, the PDF is the chance that you get uh, a specific probability, right? So that was what we did in the previous question, right? The chance that exactly one was white, or exactly, say, five were white, right? Um, if that is what we're looking at, then we want to use a PDF, right? Binomial PDF in the calculator. If, for example, though, we're looking at a cumulative distribution, or in other words, we want to see what the distribution looks like uh, at certain points with all of the possible probabilities added together, then that's what we want to do for CDF. So this is a little bit of a tricky one, right? Because it says that we want 8 or more. So really, if we draw out that graph again, we'd want to be looking at, say, here, but this way, right? Which is kind of impossible at first glance, right? But then if we remember that we have tools with probability that we can use, right? So for example, the complement, which we know was 1 minus this probability, is this one, right? And this is something that we can look at with a CDF because we're looking at all of the probabilities before this number added together. So how does a binomial distribution actually look like? It looks, well, you know what? Let's take a look. Let's see if we can do some Google on the fly here, you know? Binomial distribution. Here you go. So it's looks fairly similar, right? Except that you see all these little small bars are kind of, this is probably a better way to describe it, right? These are the individual discrete bars instead of it being continuous across. Does that make sense? Great question. How is that not normal distribution? So it looks like it is, right? But if we see it's almost like a histogram, right? So a normal distribution is going to be a smooth curve, but a binomial distribution we see jumps, right? It jumps up and up. Whoa, that's not what I meant to do. But you see what I'm saying, right? It's because uh, it's discrete. Oh yeah, great. Okay, so let's go back to. Yep, no worries. Great. So, anyways, if we're looking at a CDF here, we're looking at all the probabilities before that combined, right? So if we can use our complement rule to say, um, to say, let's say we want to know what the chance that 7 or less, right? 7 or less, and then take that probability and subtract it from 1, right? Because that's going to get us the answer of 8 or more. So, and I think I wrote this on the next kind of slide here. The binomial CDF, which we said was the cumulative, and it calculates the chance of blank or less. So, for example, 7 or less, right? Then the complement of the CDF is then 8 or more. So the cumulative probability then, if we do binom CDF with all of our settings and 7, is whatever point, 8 something. And if we subtract that, or I guess point 9 something, right? Subtract that from 1, we get this number here. So that would be our answer. So any questions with how we did this one? It's a bit tricky, right? We still have the geometric distribution to go, but we're pretty much done after that. Great. So let's take a look. Oh, sorry, I forgot our parameters for the binomial distribution. So, you guys remember the whole summation stuff and gross, nonsense, the formula jump scare that happened, right? Well, now with something like a binomial distribution, we have another formula jump scare, but it's a lot nicer of a jump scare, right? So it's a little bit easier, where we have the um, mean of this distribution it's pretty simply just the number of trials times the probability of success. And then square root, a square root of NP times, so the square root of the number of trials times the probability of success times the probability of failure is going to be your standard deviation. So if we calculated that, we would find that 10 times 4.5, or sorry, 10 times 0.45 is the answer, right? 4.5. And then the standard deviation is just going to be square root of 10 times 0.45 times 0.55. So that would be these answers here. So any questions with how we did that before we move on to the geometric? Again, pretty simple. This stuff I believe is on your formula sheet. So if I'm correct, if I'm wrong, somebody can correct me, but I think it is. So you guys can take a look at that. Okay, geometric distribution. So this is what we all came here for, it sounds like. So very similar to the binomial distribution, right? It's just that instead of having a fixed number of trials, we're looking for the first occurrence of a given outcome. So for example, if we're looking at the white cars again, at what point is the first white car going to happen, right? Or in other words, what's the probability of getting our first white car at the second car, for example, right? So that's what this geometric distribution is going to give us. And it looks a lot nicer, right? There's no chooses in here. It's nothing complicated, right? So hopefully it's pretty straightforward. So, any questions with how the idea of the geometric distribution works before we go on to an example? All right, let's do it then. So, question. We are watching cars go by again and again and again, right? And note that the chance of white car is still 45%. So, what is the probability that the first white car is the second car to go by? Well, the way we can visualize these kind of geometric distributions is very similar, right? We can visualize the first one and the second one, right? So we're going to stop when we say, when we get to the place that we are looking at, right? The second car. And then what we're going to do is say, well, all of these need to be failures, right? In other words, all of these need to be not white, and then this one needs to be white, right? So if this was for example, the third car, we'd go, okay, well, we need to go these two, the first two need to be not white, and the next one needs to be white, right? So we'll say no, 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 no. Sorry, no, no, yes, right? But of course, we're looking at the second car here. So all we need to do is say, well, the first one's going to be not white, and the second one would need to be white then, right? So at that point, all we need to do is, well, say, okay, well, we know the probability of this one not being white is 0.5. 0.55, and this one being white is 0.45, right? And because they are independent of each other, we can just simply multiply them together, and that would be our answer, right? It's a lot easier than binomial, hopefully. How do we feel about that? Straightforward, right? Cool. Great. Just to kind of illustrate this in the formula here, we had the 0.55 was this, right? We raised our probability of failure to the number that we're looking at -1, right? Or in other words, this was to the 1, and we multiplied it by our success. Did we cover standard deviations and means in geometric? We didn't do it in geometric, but binomial is this right here. So the mean for the binomial is the n times p, and the standard deviation for the binomial is the square root n times p minus 1. So pretty straightforward to implement. If all we need to do is do that, we can pretty much plug and play. Say 10 times 0.45 is 4. Yes, sorry. 1 minus p. Thank you for pointing that out. That's a typo. That's my bad, my bad. It's late. It's not even that late, but yeah. Thank you. All right. So going back to this, yes, and you're right, it's on the front of the sheet as well. So going back to this, we said we raised the number of failures. So for example, if this was 3, all we need to do is raise the 0.55 to the 2, right? Because we have 2 failures and then 1 success. So that would be how we'd find that out. Yeah, I agree, right? All right. So that would hopefully that makes sense. Let's see the answer. Great. And we can go ahead to the next problem. So we're watching cars go by again. And note, it's the same first sentence. I don't know why I keep reading it. What is the probability that the first white car is after the third car that goes by? So, what we're looking at here is after the third car, right? So we're not looking at what is the probability that the first car that goes by is the third car. We're looking at what's the probability that it's after the third car, right? So, um, there's a lot of different kind of ways to do this. But there's one really easy way. Great. So Hi says 0.55 to the 3 times 0.45. That is a great idea. Let's see what that would mean, right? 0.55 to the 3 times 0.45. So what this means is we have the first 3 cars being failures, right? X, X, X. 0.45, RS is doing it correctly, but for the recording, we'll still do it. So uh, this is the first 3 cars, and then we're saying that that's going to be failure. And then this one is success. But that's not what we're looking for, right? We're looking for after the third car, which means it could be the 4th car, the 5th car, or the 6th car, right? Yeah, you're good. No worries. Um, yeah, so you could do the whole, find the geometric CDF, of of this and do 1 minus that, right? But I think an even easier way to do it would just be to say, okay, well, all we're looking for really is that the first 3 cars are failures. We agree? So it doesn't really matter what happens after this, right? But as long as the first 3 cars are failures, we're good. So in order to find the first 3 cars being failures, all we need to do here is just say 0.55 to the 3. And that's going to give us the probability that the first 3 cars are failures, right? Because again, the idea is if the first 3 cars are failures, then it doesn't matter when this happens, right? We can find the probability of the first 3 being failures, and that works. So CDF um, is what we'd want to do here because remember PDF is the particular. PDF is particular, right? It's particular probability. The PDF is the particular probability, right? Lots of alliteration to help you remember. The CDF is the cumulative distribution. So what the cumulative means is um, the additive distribution, or in other words, the adding all together the probabilities of the first one being white and the second one being white, or I should say the first one not being white, the second one not being white, the third one not being white, right? So if we have the cumulative distribution, then what we see is we'll have okay, let me put it this way. We're looking for the specific, instead of specifically saying we're looking at the third car, we're looking for anything after the third car, right? So if we reverse that, complement it, and say 1 minus everything but the third car, then that would make it cumulative. But it doesn't even matter, right? Don't even worry about that. Just worry about just looking at the first 3 being failures. And that's what I think I did here. Yep. All right, let's go ahead and clear this. So the geometric distribution, yeah, so you'd have to 1 minus that. right? And then you reverse it. That's what I'm saying with the complement, if that makes sense. All right. So the parameters for the geometric distribution, again, even more simple than the binomial distribution. The mean is just going to be 1 over p. Square root is going to be sorry, the standard deviation is going to be square root of 1 minus p over p. Any questions? Maybe let's have you guys do this last little bit here. Can you guys find the mean and standard deviation? It's just plug and play, right? Yeah, exactly. So so 1 over 0.45 is going to give you your mean, and then the square root of 1 minus 0.45 over 0.45 is going to give us the standard deviation. So that would be that. So you guys didn't need to do it. I'm not going to make you do that just because it's really easy, right? Yeah, it's just easy standard deviation. Yeah. Yeah, for the first time in forever, right? This is actually like a digestible standard deviation formula. But get ready. These formulas are a lot easier than the continuous ones. So get ready for chapter 5. Okay. Any other questions? I think that's it. So yeah, any other questions? I'm gonna leave this form in the chat. If you guys want to fill it out, you're welcome to. It's just kind of helping us improve our lecture feedback, our lectures through lecture feedback. So yeah, everything from the environment to kind of the specific slideshow to the questions, that kind of thing. Are there AP Music lectures? Yeah, yes, I will be hosting an AP Music Theory lecture. Uh, I'm pretty busy this semester, but I do think I scheduled one at some point. Let me see if I can find it. Music. Oh, is it not scheduled, huh? Let's see. Music theory, here it is. So this is going to be on the 4th of May. And then I might be able to do one more. So that'll be the oral multiple choice, and then I might be able to do one for the free responses as well. How cooked am I? It didn't seem like you were super cooked today. But keep working on the whole course, but especially on the later chapters, I think is a good idea. Are the formulas on the formula chart? Yes, I believe somebody said they were, except they don't probably have like the choose stuff, so you just might need to remember what that actually means. Any other questions? If not, then again, thank you guys so much for joining. This is also I'll link you guys this resource as well. See if I can grab this. This is the pretty similar YouTube video to kind of what I kind of based the lecture off of. I kind of condensed what he did in 3 videos into one lecture. So take a look if you want more details there. You're welcome to use that, obviously. He's a good teacher from what I recall. And he also does more like specific AP stuff as well. All right. If there's no other questions, then again, thank you guys so much for joining. I will see you guys next time. Fill out the lecture feedback form.